17. The basic principles of ultrasound. Hello, everyone. In this lesson, we will learn the basic principles of ultrasound. Ultrasonic frequency exceeds the limit of human auditory frequency, about 20 kHz, the general term for mechanical waves. It can travel in gases, liquids, solids. Under standard conditions, the velocity of ultrasonic waves in air is about 340 meters per second, and the velocity in water is 1,440 meters per second. The standard frequency used for ultrasonic ranging in air is 20 kHz. Although this high-frequency sound wave also has good directivity, its divergence is still relatively large. Due to the dispersion, absorption, scattering, and attenuation of high-frequency ultrasonic waves in the air, ultrasonic ranging is generally limited to a short distance of tens of meters. Sonar is a kind of ultrasonic ranging sensor used in water. Since the absorption and scattering attenuation of sound waves in water are much smaller, sonar can use ultrasonic waves with better directivity and higher frequency, and the measurement range can reach the order of kilometers. Next, let's learn about the frequencies, waveforms, and probes of ultrasound. First, let's learn about ultrasonic frequencies. The propagation of vibrations within an elastic medium is referred to as wave propagation, commonly known as waves. The frequency is between 20 Hz and 20 kHz, and the mechanical waves that can be heard by the human ear are called sound waves. The mechanical waves below 20 Hz are called infrasound, and the mechanical waves above 20 kHz are called ultrasonic waves. The boundary division of sound wave frequency is shown in the figure. When the ultrasonic wave is incident from one medium to another medium, the reflection, refraction, and waveform conversion will occur on the surface of the medium due to the different propagation velocities in the two media. Next, we study the ultrasonic waveforms. Since the direction of the loss of force of the sound source in the medium is different from the direction of the wave propagation in the medium, the waveform of the sound wave is also different. Ultrasonic waves usually have the following waveforms. 1. Longitudinal waves. A wave in which the particle vibrates in the same direction as the wave propagates. 2. Transverse wave. A wave whose particle vibrates in a direction perpendicular to the direction of propagation. 3. Surface waves. The vibration of a particle is between the transverse wave and the longitudinal wave, and it propagates along the surface. Transverse wave can only travel in solids. Longitudinal waves can travel in solids, liquids, and gases. The surface wave attenuates quickly with the increase of depth. In order to measure physical quantities in various states, longitudinal waves are often used. The reflection and refraction of ultrasonic waves occur when ultrasonic waves propagate from one medium to another. At the interface between the two media, a portion of the waves is reflected back into the original medium, known as the reflected wave, while another portion transmits across the interface and continues to propagate within the other medium, known as the refracted wave. These two cases are called reflection and refraction of sound waves, respectively. Finally, let's look at the ultrasound probes. Next, let's learn about the ultrasound probes. Ultrasonic wave is produced by the oscillation of the transducer wafer under the excitation of voltage. It has the characteristics of high frequency, short wavelength, small diffraction phenomenon, especially good direction, and can become array and propagate directionally. Using ultrasonic as a means of detection, it must generate and receive ultrasonic waves. The device that completes this function is an ultrasonic sensor, which is customarily called an ultrasonic transducer or ultrasonic probe. The ultrasonic probe is mainly composed of piezoelectric wafers, which can not only transmit ultrasonic waves, but also receive them. The low-power ultrasonic probe is commonly used for detection and has many different structures, which can be divided into straight probe, longitudinal wave, inclined probe, transverse wave, surface wave probe, surface wave, Lamb wave probe, Lamb wave, dual probe, one probe reflection, one probe resection, and other special probes. The core of the ultrasonic probe is a piezoelectric wafer in its plastic or metal jacket, and the wafer can be composed of many materials. Wafer sizes such as diameter and thickness also vary. Therefore, the performance of each probe is different, and its performance must be known in advance before use. The picture shows the structure diagram of the piezoelectric ultrasonic probe. Piezoelectric ultrasonic probe is mainly composed of piezoelectric crystal, absorbing block, damping block, protective film, and so on. Whether it is a straight probe or an oblique probe, generally it cannot be directly placed on the measured medium, especially the rough metal surface, and move back and forth to prevent wear and tear. For this reason, the air between the contact surfaces must be squeezed out, so that ultrasonic waves can smoothly incident into the measured medium. In industry, a liquid substance called coupling agent is often used to fill the contact layer and play a role in transmitting ultrasonic waves. Commonly used coupling agents are oil water, engine oil, glycerin water, glass glue, chemical paste, etc. The thickness of the coupling agent should be as thin as possible to reduce the coupling loss. Usually, the coupling agent is required to be non-corrosive to the workpiece, non-toxic and non-harmful to the operator, not easy to burn or pollute, and convenient to erase after testing. In this lesson, we have learned the concepts and basic principles of ultrasound. After class, you can find information to learn what applications ultrasonic sensors have in life. That's the end of the lesson. See you next time.